Greetings and welcome to another exciting lecture in geomorphology. Today we're going to be talking about a very important fundamental concept in the world of geomorphology, and that's geomorphic hydrology. Today's lecture is going to be all about water for you. I'm really excited for this lecture because really this links some critical aspects of our ability to understand the surface of the earth and what surface environments look like. Because when we look around the earth, if you compare the Mojave Desert, the Yellowstone National Park, to the Aleutian Islands, to the Columbia River Basin, those landscapes look very different. Part of those differences are driven by just the amount of water associated with those landscapes. And so because of that, it's really important to understand the profound influence that hydrologic processes have on geomorphic processes. So the goal here is to kind of expand that out today. And just for an example, when thinking about how important hydrology is for geomorphology, have a look here at the Potomac River. It's all working. Here it is, the Potomac River right here. Looking at the Potomac River, this is a nice looking river here. We've got a nice bedrock channel, and we can think about essentially when is geomorphic work done on the channel? Like right now, we think we're getting a lot of erosion in the channel right now associated with water flowing over. So what drives erosion? Is it days like this where you have kind of more standard water flow? Or is it after large flooding events? So let's say we've got Hurricane Isabel from 2003. Let's look at what the Potomac looked like at this time. All right, repeat photography here, very, very different. This is Great Falls on the Potomac, and our discharge is 4,500 cubic meters per second. And so there's an immense amount of power associated with water of this volume flowing over the landscape. And so perhaps it's these large flooding events that actually shape the channels that we see associated with bedrock rivers. And so because of this, we really need to watch out and pay attention to hydrology and how water moves across the surface of the earth. Okay, so that, oops, got my question down here on this side. When is geomorphic work accomplished? All right, so we're going to start very simply with the concept of precipitation. So when we talk about rain falling out of the sky, let's stick for this discussion as to liquid water. Take a hydrology class and you can talk about rain, sleet, snow, and other forms of precipitation. But let's just for now talk about precipitation in the water form. When we think about geomorphic work and like how that water is going to flow over the surface and the effects it might have, we need to think first about the duration, which is how long it rains, the intensity of the rainfall, how hard it's raining. Is it raining just a small amount, maybe a millimeter per hour, or is it 10 millimeters per hour? So intensity is going to be very, very important. And next up on our list is we can set up what's called an intensity duration threshold. And these are very, very important because this can kind of set up boundary conditions on a hill slope between a hill slope that's about to fail and one that's stable. And so if we cross a threshold, we can think about a threshold as being on a hill slope. We have a threshold where we have a safe slope, and then we cross a threshold and that slope is unstable and it fails. So what am I talking about here? Here's what this threshold would look like. In this case, we're going to talk about rainfall intensity. So here's rainfall intensity on our y-axis from not particularly intensive rainfall, a millimeter per hour of rain. So, the thickness of your thumbnail every hour, all the way up to maybe 100 millimeters per hour. And so that would be a very, very high rate. So that's our y-axis here. And then our x-axis is going to be duration, how long it rains. Is it only raining for a couple of minutes, or is it raining for an extreme amount of time? And so we can actually define a threshold where below so here's our threshold. It's this line right here, threshold right here. And below that threshold, down here, let's try this. Down here, we have happy, stable slopes. So what this means is that when it's raining at a particular intensity, let's say at 1 hour, it's been raining at an intensity of 10 millimeters per hour. As long as we keep that intensity at 10 millimeters per hour, and we don't cross this threshold, which would mean raining up here of maybe an entire day, as long as we keep below that threshold, we're going to keep our slope stable. But let's say it keeps raining for several days at this intensity, and then at that case we'll cross the threshold. We'll now be on the unstable side here, where we might have a slope failure event. So this this threshold can be really important in understanding processes on hill slopes. And here's an example of this right here. This is Winsagon, which is in the Philippines, and this was a village here. And in 2006, there was a very, very intensive rainstorm in February, and we had intensive rain of fairly long duration, of several days of heavy rain. We crossed that threshold, and we had basically a slope failure, which ended up creating a landslide, and that landslide deposit covered the floodplain at the bottom of the valley. And it buried more than 350 houses and killed more than 1,000 people. So this is very, very important, understanding these thresholds in the landscape. Okay. When we think about hydrologic systems, we always need to keep in mind that humans are going to have a really, really important impact on those systems. So here we're looking at, again, something we've talked about a little bit already in class. Let's say that you put a bunch of cars on a grass lawn here. We start to compact that soil, and it's no longer easy for the water to flow down in. And so we end up with more surface runoff. And so our sewer systems and our drainage systems are designed for a certain amount of runoff based on the amount of roads we have. And so if we essentially create more of those roads, we could be overwhelming those systems. Here's a picture from your textbook looking at these, how we can measure these changes, these organic changes. So here we've set up essentially an experiment to artificially rain on this landscape and see when we start to generate runoff. And here, collecting the runoff in this bucket down here, how much. Some of you might remember I've talked about this. This is some work that I did back when I was an undergraduate working at the University of Vermont, and had the opportunity to work out in the Mojave Desert at the Fort Irwin National Training Center. And we were interested in how military activities like driving tanks influence these surface processes. Here we are setting up one of these infiltration tests where we're going to be measuring how much it rains, how much you need the rain to cause runoff. And we can compare that between sites where there is not been military impacts. Okay, so a very important term we need to introduce when talking about hydrologic events, whether it's flooding or rainfall, is what's called a recurrence interval. And a recurrence interval is essentially the probability that of an event of a certain size happening in a specified amount of time. So here, my textbook definition: probability of an event occurring based on the average amount of time that passes between events. Okay, so this is where you've probably heard these terms before. This is where the terminology, the 100-year flood, comes from, right? The 100-year flood is basically the size of a flood we would expect to happen once every 100 years based on statistical analyses of previous floods. So how do we calculate our recurrence interval? It's pretty darn simple here. Our recurrence interval is simply equal to our number of observations plus 1 divided by the rank of those observations. Essentially, let's say we get a bunch of rainfall events for how much it can possibly rain in a day. And so we calculate this, and then one year the most we got was 2 inches, another year we got 3 inches, and another year we got 1 inch, and another year we got 4 inches. We're just going to rank those from the highest to the lowest, and then we can estimate the recurrence interval of, say, how often it rains 2 inches based on that equation. This is what we call the recurrence interval, and it's very important to understanding the likelihood of a hydrologic event, rainfall or precipitation occurring of a given size. Okay, The other term we often use when talking about recurrence intervals is essentially the probability of the event occurring in any given year. And so the probability of that event is equal to 1 over the recurrence interval. So we're going to have a chance to work on these in some assignments in the coming days, but these are kind of the equations we use to start to quantify how likely an event is of a certain size. So how we use these is we generally make a plot, an XY plot that's going to have our recurrence interval on the x-axis and then whatever our hydrologic variable is on the y-axis. So here we've got, again, that maximum amount of precipitation that we can have in a given day. So basically we can maybe have 100 years of data where we're looking every year the maximum amount of rain you get in a day. You essentially plot those and we can look at the recurrence interval where the recurrence interval for an event that happens, once every 10 years might be every 10 years you can expect to get roughly about 80 millimeters of rain. So this is how we use that recurrence interval. The interesting thing about recurrence intervals is generally you start off by just making estimates based on the total number of observations you have. So in this case here, maybe we've made 20 years of observations, and so we can estimate what our recurrence interval is for a particular event based on those 20 years of data. Now the cool thing is we can just do what's called an extrapolation, and we can fit a line through our observations so that we can extrapolate and estimate maybe what the recurrence interval is of a larger maximum 24-hour event, maybe one that happens every 50 years. Of course, it's really kind of dangerous when doing these types of extrapolations. You have to think about how you're going to fit this type of data. In this case here, we're looking at a different curve with a different type of axis, and a log axis in this case. Excuse me, we were looking at a log axis on our previous slide, and now we're going to look at this with a linear axis. And we see that really we've got a large amount of time where we don't have any observation. When we don't have those observations, that can be we just don't know how often or what the size is of those large events. So this is extrapolation, and this can be kind of tricky to do. And so when we're making estimates based on recurrence intervals, we have to remember that recurrence intervals are based on statistics of past events, right? It's just based on what's happened in the past. It doesn't necessarily tell you about what's going to happen in the future, just a statistical likelihood. And there's another complication we have to worry about as well. So let's look at some data here from a fairly recent precipitation event. And that would be Hurricane Harvey that we introduced at the beginning of the semester back in 2017. And we got some very, very significant rainstorms associated with this hurricane pushing onshore and dumping massive amounts of rain in the Houston area. So here it is, Hurricane Harvey 2017. And what I'm pulling up here is looking at our exceedance probability, how often you would expect a rainfall event of this size of the total amount of inches, where we got many tens of inches or over 10 inches of rainfall here associated with Hurricane Harvey. And notice here that in places, let's go to Beaumont, a little outside of Texas here, we're in the purple here. That exceedance probability, what we're saying is we would expect this event to happen only once every 1,000 years based on historical events. So one would think, hey, that type of event doesn't happen very often. But does that mean that you just be like, okay, we're set. We don't have to worry for another 1,000 years. We'll never have a rainstorm like this again. And likely we'll never have flooding to this degree. Well, have we made 1,000 years of observations? No, probably not. We haven't been recording precipitation values here for 1,000 years. This is an extrapolation based on using exceedance probabilities like you saw in the previous graph. So that can be really dangerous. And we saw that just a couple of years later in Tropical Storm Imelda, just in 2019, that we actually got in that Beaumont area again, a huge amount of rain. And we saw that again, this was a precipitation event that we would predict would happen maybe only every 1,000 years. So again, this really highlights um, the dangers of making these kind of predictions based on past events, especially when looking at such cases. Just don't have that much data out at these extreme, events to really know what the distribution looks like. And this is really important when we're communicating science to the public. We have to make them understand what these and help them to understand what these, right? The 100-year flood, we don't want people to feel safe, right? We don't want people to be like, oh, we just had a 100-year flood last year. We don't have to worry for another 100 years. So these terms carry a lot of weight with them, and we have to be careful in how we use them. Another really important point is, again, when we make another assumption we make when using exceedance probabilities and recurrence intervals is that essentially you're assuming that the past, events that have happened in the past, have the same statistical distribution as events that will happen into the future. We're assuming that the past is a good model for the future. And perhaps that's not necessarily the best assumption we can make. For example, what if your baseline, what if what's happened in the past is actually shifting? And perhaps that's associated with things like climate change. Like maybe we've had increasing average temperature, and as we have increasing average temperature, whoops, go the way I want, there we go, increasing average temperature from a previous climate to a new climate, if we look at the distribution of whoops, I'm going the wrong way again, sorry, the distribution of flooding events associated with a given, a given distribution, right? That we expect a certain size flood based on 100 years of data. But what if, as we warm up the atmosphere, we're able to put more water into the atmosphere, and so potentially we can have larger rainstorms and have more significant flooding. So we're shifting that baseline. And so here in this case, we used to have just this way, we used to just have kind of large floods here, but as we shift that baseline from to here, we end up making the 100-year events even larger events. And so this is a problem as well when we talk about recurrence intervals. Okay, moving on. So that's a nice statistical way we kind of quantify precipitation events. The next thing I want to talk about is what we call the global water balance. We'll get to the global water balance next. Okay, so thinking about the total amount of water at the Earth's surface and how much it rains versus how much evaporates away is really important, because that's going to drive the types of weathering and erosion we see in different climates. What we're looking at here is essentially a water balance based on a budget that actually goes from 0 to a high number versus an actual negative number. So how the heck do you do that? How do you have negative water? Well, the answer is right up here, is that we're looking in this water balance as our precipitation minus the potential evapotranspiration. And so potential evapotranspiration is how much evaporation and transpiration, that's the water coming out of vegetation, how much would we predict if there was enough water? If it rained that much, if it rained 10 inches a year or a meter a year, would the plants use all that? So if the plants would use more than that, then you would end up in those negative numbers. So where do we see a negative water balance? It's in our dry regions that we find in the subtropics, above the tropics themselves, the Sahara Desert, the North American West here. These are locations where we end up with these negative values because we have essentially, we're close enough to the equator that it's relatively warm in temperature, but we don't get the precipitation. And we'll talk later in the semester about why it doesn't rain here, associated with Hadley cells. But for now, let's just say we know these deserts are dry, so we end up with a negative water balance. So generally what we see with that water balance is that it's positive at the equator where it's warm and wet. And in the subtropics, it is in the negative as we move into those dry and hot areas. And then as we move into the mid-latitudes where we get more precipitation, then we end up with that positive water balance again. Okay, So I mentioned this term. Let's look at kind of a hydrologic budget and introduce this term more formally. When I'm talking about evapotranspiration from a landscape, we're talking about essentially when it rains onto the surface, how much of that water either evaporates back up to the atmosphere, where you go from a liquid back to a gas, or transpiration, that amount of water that's moved out of plants. And so that's going to be really important. Our evapotranspiration is important because what happens is that influences how much water is going to be left to flow over the ground, or how much is going to be able to flow as groundwater. Okay, so having a look here, when we think about water budgets now and water balancing, we're going to have precipitation that's bringing water in. And then we're going to have some of that precipitation that gets to the ground and ends up in groundwater and flows down. We'll have some that flows over the surface that we call overland flow. And then what doesn't end up in river channels is that evapotranspiration, water that's transpired off trees or uh, uh, evaporated off the surface. I'm showing you here the humid example first. As we move forward, we can think about how this differs between a dry region and a wet region. So humid here, we looked at this. In an arid region, we're going to have less transpiration as we have less vegetation, and we're going to have that precipitation, and we'll end up generating overland flow again. And potentially, as it rains less in the arid regions, what we have is a disconnect between the surface and the water tables beneath the surface. All right, and we're back. Sorry about that. Had a little bit of a delay there, but hey, look what I got to do. I got to change the color of the text here so that you could see what I'm talking about. That the next point I want to make is about infiltration. And so infiltration is a very, very important concept when thinking about hydrologic processes and how they interact with surface processes. Infiltration is the rate at which water moves from the surface into the subsurface. So we talk about an infiltration rate in length per time, whether it's millimeters per hour, centimeters per day. That's kind of what we're talking about when we talk about infiltration rates. And so infiltration is going to be a really, really important concept here. We're looking at our slide. Where's my, there we go. Got my pen here. Infiltration happens right here. So, oh, sorry about that. Let's get the marker out here, our pen out. So we have water that comes to the surface. When it hits the surface and lands on the surface, that movement down into the subsurface is infiltration. And so that's part of what we call kind of the water cycle, the water balance. Where here we're looking at the amount of water coming here. There we go. The amount of precipitation, the water coming onto a landscape. And so depending on the rate at which we have precipitation landing on the landscape, depending on that infiltration rate, if it rains harder than we can infiltrate down into the soil, we're going to end up with what we call overland flow, where we pool water at the surface. Another part of our water balance here is going to be once that overland flow makes it down into the river, that's going to be kind of runoff going down in streams. And the water that's going to be returned to the atmosphere is going to be evaporation from the land or transpiration from the trees. Okay, that water that makes it down into the subsurface is going to then percolate. So percolate is the movement of water through the ground. Talked about infiltration earlier. That percolation, that water will eventually reach what we call the water table. Now, the water table is a really important concept. The water table is the difference of where in the ground, in the subsurface, when we're below the water table, any pore space, any space between pieces of dirt is completely filled with water. Whereas above the water table, we have what's called the vadose zone, where your pore spaces are going to have a mixture of water and air in them. So that's what we call the vadose zone, or the soil moisture zone here. Okay, so that is our our kind of overview of kind of, sorry, here, overview of kind of a water balance for where water moves along the surface. Um, when we talk about things like infiltration, the rate at which that water moves into the soil, it's going to depend very much on the type of soil. And so here we're looking at some typical infiltration rates in millimeters per hour. And so if we have a very sandy soil, it's going to have very high infiltration rates, say 30 millimeters per hour, versus a really clayey soil where there's not much space, there's not much pore space, and so it's hard to get that water into the soil. Okay, so that's what we call infiltration. And here what we've got is a setup for how we study, how we kind of quantify those infiltration rates. So what we've done here is we've kind of used some roofing flashing to put an outline along part of the ground. So we kind of just pound into the ground this metal flashing. And then what we do is we get a backpack sprayer. So here's Luke, yeah, or no, is that Kyle? That's Kyle, or is that Luke? That's Kyle Nichols, who is basically raining down on the landscape here. So we're putting water onto this test plot, and what we're quantifying is how much soaks into the ground, so how much goes down into the ground that we don't see, versus how much runs off the surface that we can collect in this bucket right here. And so we can then calculate that infiltration rate because we know how much we're raining down, how much is running off, and so the rest is going into the soil, and that's how we calculate infiltration rate. Okay, generally we see that infiltration rates change with time as we start to saturate the material, the porous material. And so if we have at the beginning here, the time of the start of the event, we start at the beginning of the event, we generally see high infiltration rates at first. And so as we start to saturate the soil at the surface, that infiltrate decreases as the storm goes along. And the blue line here is our runoff, the amount of runoff. And so here, our runoff starts off really low as the storm gets started because our infiltration rate is high. And then what happens is our runoff increases over time. And then eventually, once we reach the steady state saturated soil, what's going to control our runoff rate, these little squiggles up here, are associated with variations in rainfall. So the green line is the amount of rainfall. So here we've got a little lull in the storm that causes a decrease in the amount of infiltration. Oh, sorry, the amount of runoff. Sorry, our infiltration rate at this point is staying. Okay, so this is what that runoff can look like. So once we exceed infiltration, once we can no longer put water into the soil, then you end up with runoff along the surface. So here's this overland flow right here. Okay, moving on, a couple of terms I want to introduce from the world of groundwater hydrology. And so we don't need to go into great detail with this, but these are just some terms we use when talking about the movement of water beneath the ground. And if you're really interested in this, I encourage you to take a full class on hydrology. So again, remember that we get precipitation at the surface and it rains down, it hits the surface, it starts to pool here. Some of that infiltrates into the ground and then it moves, it percolates down. And then once we hit the water table, that water table is essentially the saturated zone. Sorry, it's kind of missing there, but the saturated zone where all of our pores are completely filled. Above that is what we call the capillary fringe. And so the capillary fringe is where we actually have this kind of action where the groundwater is moving out, even though it's not completely saturated. This is kind of like the capillary fringe, like you see wetting, like say you've got a paper towel and you dip it in water and that water moves up the paper towel. That's the same type of capillary action that we're seeing as we see oil itself. So we end up with that capillary fringe, and then this is kind of our pore space that contains some air and some water, that vadose zone that I called it. Okay. How this relates to geomorphology in a really important way is where the groundwater table is, this water table. where that intersects the surface is going to be really important for understanding how our stream. So in the case we've shown you here, the groundwater table is at the surface, and so here, where the groundwater table hits the surface, we have a stream. That's not always the case. That would only be in humid regions. In arid regions, because it doesn't rain much and we have high evapotranspiration rates, our groundwater table is significantly lower. And so at this point, any water in the stream has to be coming just from overland flow. And once the water is in the channel, it's actually going to percolate, infiltrate out of the bottom of the channel. We call this a losing stream. Opposite of that would be a gaining stream. A gaining stream, even if it's not raining, even when it's not raining, there's water in the channel, and that's because we have groundwater that's flowing into the channel. So that would be a gaining stream. So gaining versus losing stream. Essentially, it depends on whether your groundwater table is at the surface or below the surface. So surface here, a gaining stream, and then below the surface down here. Okay, moving on a little bit. There's one last term I want to introduce and build on here because it's going to be really, really important. And that's essentially starting to think about how quickly and what drives water movement underground. And so we can think about this as essentially what we call Darcy's Law. I'll introduce here in a second. But what we're interested in is if you have water that is moving in underground in porous materials, how quickly is that water going to flow? And so we can set up an equation here where we're going to be looking at essentially our discharge out of some unit of soil, how much water moves out of that soil is going to be related to a couple of things here. It's going to be associated, of course, with the size, the cross-sectional area of our column of soil, and that's right here, our cross-sectional area. But what's going to control how quickly water moves down through this hypothetical tube are two other factors. The first here is what we call hydraulic head. And that's essentially the energy head associated with gravity. And so in a landscape, we see that because of gravity, water flows from a high point down to a low point. And so we can quantify that as the total energy of water at a point. That's the hydraulic head, the total energy. And we can often measure that total energy from a reference point like sea level. So we'll talk about the head being the amount of elevation above sea level we are. When we're talking about how water is going to move through the soil, it's not necessarily the total head that's important, but it's going to be the change in hydraulic head between 2 points. So here, as we go down in elevation, we're losing head. And so this difference in hydraulic head is going to, and over what distance we lose that hydraulic head is going to determine how quickly that water is moving through the ground. Does that make sense? So if we think about this equation here, if you have a greater distance, if this number is bigger in the top of our numerator here, then our rate of flow is going to go up. And that makes sense, right? If it's steeper, you're going to have more gravity working on it. That rate of flow is going to go up. So that would be our change in hydraulic head. So we call that the hydraulic gradient or head difference. So now we've talked about the hydraulic gradient, the head difference, and we talked about the cross-sectional area. The last thing that's really important for understanding how quickly water moves to the ground is what we call the hydraulic conductivity of the soil. So hydraulic conductivity is essentially how easily you can pass that water through your porous material. So what we're looking at here is two examples here. In the first example here, let's say that this is a less dense soil and water can move really quickly through all these pathways. So you might have a very high hydraulic conductivity. That's going to be very different if you've got a very dense soil where it's a more tortuous pathway for the water to flow, and it's going to flow around all these tightly packed particles. And in that case, it's very tortuous. The water goes up and over one particle and then down under another, then up over one and down. And so in that case, when you have kind of a lot of flow pathways that are really small, then that water can't move very fast. our hydraulic conductivity goes down. So high conductivity, low conductivity. There's two variables that determine how what that hydraulic conductivity is. The first is our porosity. And so porosity is just when we're thinking about a material like dirt, porosity is just how much, if we have a volume of dirt, how much of that volume is dirt and how much is air. So generally when we have high porosity, we have very higher hydraulic conductivity. Whoop. Our other term here is permeability. So permeability is essentially how well connected are those pores. When the pores are really well connected, you have high permeability. So when we think about hydraulic conductivity then, a low hydraulic conductivity is going to be a material where we have no pores and we have no way to connect what little pores there are. We move up here, maybe we have high pores, but they're not well connected. And so this would be a low permeability, but highly porous material. And then finally here, where our pores are all connected, we have highly porous, impermeable material. This would have the highest rates of hydraulic conductivity. We can think about hydraulic conductivity kind of in four boxes. Low porosity, low permeability here first. And so that's going to be like a crystalline rock where we have very, very few crystals, void spaces in between the crystals, and they're not connected. And the water flows very slowly. Next up would be where we actually have a lot of pores, but they're poorly connected. And so maybe you've got a clayey layer, and so the platey clays kind of lock off all the different pores. Then it's hard to move any water actually through those pores. They get stuck. So that would be have a lower hydraulic conductivity. We can have a low porosity and low permeability, like a glacial till, where we pack everything together. And in that case, a glacial till, you got big stuff and little stuff. The little stuff fills in all the pore spaces from the big stuff, and it's still really hard to pass the material. And then our last one here, high porosity, high permeability. And so in that case, we've got like a sandy quartz sandstone. In that case, you've got lots of pores, and those pores are connected, and the water moves through them really quickly. And so kind of with this understanding then of hydraulic conductivity, we've essentially defined what's known as Darcy's law. And Darcy's law it describes that flow, how quickly water passes through porous materials. And so a big one here for us is that height change, that change in hydraulic head, and over what distance. That's going to be important. And then the other really big deal is what the material is. So is that material highly porous or not highly porous? And those are going to define how quickly the water moves through. All right, this concludes the first half of our lecture on geomorphic hydrology. Next time we'll come back to geomorphic hydrology, and we're going to talk about hydrologic flow pathways. That's where we're going next with. So thank you very much. Have a great day, and we'll talk to you soon. Bye.